I have shown you earlier how to calculate the shear strength of the EPS geofoam under various densities of EPS geofoam material. Now, I will show you how to calculate the shear strain of the EPS geofoam material. So, we have to calculate the shear strain, and that is, let us say, comma of the geofoam material. So, the shear strain is equal to U this divided by T, where U is equal to deformation at peak shear load in millimeter. So, deformation at peak shear load in millimeter, and this is the T. So, T is the thickness of core. This is thickness of core, that is in millimeter. So, this shear strain, that is gamma, you can determine that deformation at peak value is 4.67. So, this is 4.67. Okay? And this divided by the thickness of the sample is 25. So, this will give the shear strain of the EPS geofoam is 0.1868 millimeter per millimeter. So, you can see here from this table in the slides where I explained you earlier. Here from these slides you can see that deformation at peak load is 4.67. Okay? So, you have calculated deformation at peak load at 4.67. So, here I am showing that deformation at peak load is 4.67, and T, the thickness of core, is 25, and that is why the shear strain value is 4.67 by 25 is equal to 0.1868 millimeter per minute. So, you know how to calculate the thickness, how to calculate the shear strain of the EPS geofoam material. Next, I will show you that how to calculate the G value, modulus value. Now, you know del P by del of U is equal to 855.88, and the thickness is 0.025 meter, and you know the length of the sample is 0.3 meter, and B is equal to 0.05 meter. So, you can calculate from the earlier equation, you know delta P G is equal to delta P by delta U, that means 855.88. So, 855.88 into T is 0.025. This divided by length is equal to 0.3 into the B is equal to 0.05. So, this G will be equal to 1426.467. This is kilopascal. So, you can calculate the G value, and this value delta P by delta U, which I have shown you from the earlier table, which is shown in the in this table. You can see delta P by delta U is equal to 855.58 for a EPH density of 20. So, core CR modulus value is 1426.467, and here it is shown 1426.267 in 47 kilonewton per meter. This is the modulus value. So, you know that how to determine the modulus of the EPS geoform material. So, from this shear strength of the EPS geoform, you can calculate what will be the shear strength of the EPS geoform, what will be the strain of the EPS geoform, and also that what will be the modulus of the EPS geoform material. Next, we will discuss the breaking load or fractional properties of the EPS geoform material. Because fractional property of EPS geoform material is important in the different application of civil engineering. How you can make use of the EPS geoform in civil engineering project, for that you require what will be the fractional properties. So, to calculate the fractional properties of the geoform material, so here is main objective of this to determine the breaking load and fractional properties of geoform. So, this is a 3-point method and 4-point method are used to determine fractional strength of the EPS geoform material. So, here I am showing this curve is the 3-point method. So, you see here this one is the geoform specimen under 3-point method, and you are applying the load at the middle of the EPS geoform here, and it is supported by this. So, this length from here to here, this capital L is equal to 100 millimeter, and this is the sample, this is about 20 millimeter, from here to here is the 20 millimeter. So, this is 3-point method. Similarly, you can also perform the test under 4-point method. Here is the 4-point method. This side is the 4-point method, and this distance from here to here is L by 2. This is, let us say, L1, and this is L1, and this is the L, and here also this distance is about 20 millimeter, and this small L is equal to 100 millimeter. So, this is the size of the specimen in which you can perform strength of the EPS geoform material. This test specimen, as I told you, here you can see the test specimen should be the 300 by 100, and this is 25 millimeter. This is EPS geoform specimen. So, you can cut any sample, that size will be 300 by 100 millimeter by 25 millimeter, and you can perform the test under different densities of the EPS geoform material. Here I am showing the sample with the different density, that is fractional strain test specimen, and density for 15 kg per meter cube, this is 20 kg per meter cube, 22 kg per meter cube and 30 kg per meter cube. So, these test that what you require the apparatus and accessory. So, you require testing machine, you require what will be the fractional test assembly. So, here you can see that fractional test assembly for geoform, plant length is about 250 millimeter, here 250 millimeter, and this all this equipment has been fabricated indigenously in IIT Bombay, and this test has been performed. So, this is the fractional test equipment. Now, the testing procedure for this, install the assembly in the testing machine, apply the load to the specimen and record the load deflection data till failure of the specimen. So, then how to calculate the stress, fractional stress of the geoform material. So, for the calculation of the EPS geoform material, we are showing some calculation. Maximum fiber stress, let us say S. S is equal to 3 into P into L, this divided by 2 into B into D square, where S is equal to stress in the outer fiber, that is in kilopascal. What is P? P is the load at a given point, on the load deflection curve, okay, that is in Newton. And L, this L is the support span, and B is the width of the beam tested, that is meter, and D is the depth of beam tested, that is meter. So, you know this equation, what you call maximum fiber shear stress value. So, if you know that what will be the P, what should be the L, and you know that what will be the width of the beam and what will be the depth of the beam. So, knowing this value of P, L, B and D, so you can calculate what will be the maximum fiber stress, that means S. Similarly, you can calculate the maximum strain value. Maximum strain maximum strain you can determine, that is epsilon. So, the maximum strain in the outer fiber occurs at midspan, That means that maximum strain will be equal to 6 into d, capital D into small d divided by L square. So, this is the equation for the maximum strain value, where you know that epsilon is maximum strain at the outer fiber, you know. So, D is this is maximum strain, okay, at the outer fiber, and D is the maximum deflection, of the center of beam, maximum deflection of center of beam, this is millimeter. And L, you know that what is support span, in millimeter, and what is small d is the depth, that is in millimeter. So, you can determine that what will be the maximum strain of the EPA geoform material using this equation, that epsilon is equal to 6 dd divided by L square. You know what is d, that maximum deflection at the center of the specimen, and you know what is L is equal to support span, and d you know what will be the depth. So, you can calculate the maximum strain. You also can calculate that what will be the inertia, that means moment of inertia of the EPA geoform material. So, calculate the moment of inertia, and so moment of inertia can be calculated as I is equal to you know B d to the power q, this divided by 12. So, what is I? I is equal to moment of inertia, that is millimeter per 4, and B is the specimen width. So, B is the specimen width, that is in millimeter, and D is the specimen thickness. So, this will be the specimen that thickness. So, this is designated as millimeter. So, you can calculate the moment of inertia, and moment of inertia you can calculate within this equation. So, you know what will be the B, specimen width, you know what will be the specimen thickness. So, you can determine the moment of inertia using this equation, I is equal to B d to the power q divided by 12. So, moment of inertia also EPA geoform can be determined. Apart from this moment of inertia strain, you can also determine what should be the elastic modulus of the EPS geoform material. So, elastic modulus of geoform material, okay, how to calculate. That is, E will be equal to 148 into P into L to the power Q, this divided by I into D. So, where E is equal to elastic modulus, is elastic modulus, and this is kilopascal, okay, and D is corrected deflection, at the center of the sample, corrected deflection at the center of the sample. And I is the moment of inertia. You know, earlier you have calculated how to calculate the moment of inertia. I is moment of inertia, and that is in meter 4. And L is support span, L is equal to support span, okay, that is in meter, and P is equal to load at a given deformation. So, P is equal to load at a given deformation, load at a given deformation with the within the proportional limit of the span, and that is in Newton. So, elastic modulus, that is that E can be determined within this equation. So, you know this equation, you know that what should be the elastic modulus of the geoform material, and you know that what will be the D, that is what you call the corrected deflection. You know that what will be the I, already you have calculated earlier, that moment of inertia, and also you know that what will be the L, that are support of the span, and P is the load applied. So, if you apply this load and you know that what is the load has been applied, the sample have fell. So, then knowing the value of L, knowing the value of moment of inertia, and knowing the value of D, capital D, corrected deflection, and then you can determine the elastic modulus of the geoform material. So, you can calculate the moment of inertia, you can calculate the elastic modulus of the EPA geoform material. Now, I will show you some of the sample failure in perform the test. You can see here the different geoform, EPA geoform material under different density, 15, and this is 20, this is 22 and 30 kg per meter cube. And this is the before the test, and you can see that after the test this sample fell at the middle. So, when you perform the fractional strain test on the geoform, you can see how the sample fell here. So, it is middle of the span. You can see how the sample fell under 22 kg per meter cube EPH density when it is 22 kg per meter cube density and the 30 kg per meter cube density. So, from this test, here I am showing the same sample EPH geoform specimen after the failure. And you can calculate that what should be the fractural strength of the EPH geoform material. So, as per the STMC 20205, so when the density of the EPH geoform is 15 kg per meter cube, then fractional strength value is 149.9 kilopascal, when the and corresponding deformation is 25.41 millimeter. So, when the density of the EPH geoform is 20 kg per meter cube, then fractional strength is 211.3 kilopascal and the corresponding deformation is 33.13. When the density of the EPH geoform is 22 kg per meter cube, then the fractional strength is 240.6 kilopascal and corresponding deformation is 38.11. When the density of the EPH geoform is 30 kg per meter cube, so density fractional strength of the EPH geoform material will be about 277.0 kilopascal and corresponding deformation is 46.07. So, from this fractional strength of the EPH geoform material, you will be knowing that what the location the EPH geoform material has fell. It fell at the center of the span of the EPH geoform material, and from this test you can determine what should be the fractional strength of the EPH geoform material, what should be the moment of inertia of the EPH geoform material. You can also calculate the elastic modulus for EPH geoform material. And these are some of the property, either in the tensile strength of the EPH geoform material what you call the initial tangent modulus or the second modulus, or even then that elastic modulus of the EPH geoform or the moment of inertia will be useful for any numerical analysis or the finite element method analysis.